Okay, all set.
Okay, good. Welcome back, everyone. Good to see you all. Um, so, as I mentioned in the email announcements, there has been lots and lots of discussion so far about the Weil conjectures and the place they have inside, sort of mathematical culture, the relation to things like the Riemann zeta function, the Riemann hypothesis, all that sort of stuff. And what I'm hoping to bring across today is how you might work with some examples, how you might actually do some calculations on your own and convince yourself that these conjectures might be the sort of conjectures that are reasonable to make. So the class of examples that I want to introduce are certain objects called elliptic curves. We'll talk a little bit about their history. I don't intend to prove the Weil conjectures for elliptic curves today. I hope to just more give you a sense of what these gadgets are and, as I say, how you might work with them and play with them yourself if you're interested. But if this is a topic that interests people, then maybe there's something we can cover again next week. I'd be very happy to go back to this and actually discuss how the proof works in this case. It's much more elementary than the proof for the general Weil conjectures. It's actually quite approachable. Okay, but before we dive into any of that, let me open up by asking you all a question. Are there any squares one greater than a cube? What do you reckon? Come on, I can't be doing all the work around here.
8 9.
Very good. Yeah, and Masuda's just the same thing in the chat. 9 is 8 plus 1. Any others? Yeah, 1 is 0 plus 1. That is a square that is 1 greater than a cube. And in a similar thinking, I think we might get close to another one, which is that the square 0 is 1 greater than the cube minus 1. And let's see, it's going to go. Do I have to press right? Okay. Claim these are the only ones. 0 is 1 greater than minus 1, 1 is 1 greater than 0, and 9 is 1 greater than 8. This is a sort of classical question. This is a style of question that's been studied for, as long as people have been thinking about maths, really. This goes way back to people like Diophantus in ancient Greece. And one way to frame it is to say, well, what we're doing by asking this question is we're trying to find integer solutions to a certain polynomial equation, y squared equals x cubed plus 1. And what we've done just now is we've found a certain collection of solutions. We've found if y squared is x cubed plus 1, then minus 1, 0 is a solution, 0 plus minus 1 are solutions, and 2 plus minus 3. These are all solutions to this equation. In modern terminology, we will refer to this as finding points on an elliptic curve. But as I say, this is a much more ancient style of problem, going back to Diophantus, and perhaps unsurprisingly, this style of question that persists today, trying to find integer or rational solutions to polynomial equations, is a field known as Diophantian geometry. This particular problem was resolved by Euler in 1738, and you can find his proof in the original Latin. Well, I don't know if it's the original or a transliteration into Latin, but his proof is written in the appendix of Scoop's book called Catalan's Conjecture, and in that book, you actually have another solution that's in English, so you can compare that as well. The method is sort of known as the method of descent, which is, you may have seen something like that if you've looked at the proof of the irrationality of the square root of 2. That's a proof by descent. You sort of show that, oh, I'm going to assume some minimal solution, then derive some sort of contradiction. And Euler's proof is by descent. There are more modern proofs by descent that maybe avoid some of the weird tricks that he had to use because we have more technology these days. So I do recommend it. That's a good book. It has lots of neat ideas in it. Catalan's conjecture is a much broader conjecture about two general powers, perfect powers, being different by one. This is specifically the case, a square and a cube. All right.
Is it true that we still need the excluded middle to prove this?
Oh, that's a good question. I wouldn't know the answer to that. Does anyone happen to know off the top of their head? It's a good question. We can come back to that. Should look into that because I do not know.
Sorry, what is the question? I didn't understand the question. What is that?
It is to know if proving the statement requires the use of the law of the excluded middle.
What's that?
Is that a statement is either true or false? I mean,
Okay.
I am no logician, so I can't answer
Okay.
the questions of that level of depth. That is a good question.
It's not really important. We can continue.
Okay. So I claim that in modern language, we would call this finding points on an elliptic curve. So let me tell you what those words mean. So an elliptic curve, we would say, an elliptic curve is defined over a field K, and it's a smooth, projective, cubic curve where we have additionally chosen a certain base point on that curve. Okay, so a lot of words to unpack there, and I'm not going to unpack them all today in full generality, but we have seen some discussion before of the use of the word projective in algebraic geometry, and we've discussed that it may have some relationship with sort of compactification. You take some object and you maybe add some points or add some extra stuff to make it whatever the correct notion of compact is in algebraic geometry. Smooth, there is a precise way to define what smooth is. You can talk about the non-vanishing of certain collections of partial derivatives if you've gotten it written out in some equations. But for us, it turns out to be quite nice. So we take a general cubic, and it turns out just by making various substitutions and changes of variables, as long as the characteristic of your field is not 2 or 3, so, for instance, any finite field from size 5 or up, or a field of characteristic 0, like the rational number or the complex numbers, so only a very small number of cases where this is impossible, you can make a change of variables to put it in this specific form. So it's a homogeneous cubic equation that reads y squared z equals x cubed plus axz plus bz cubed. And the condition of being defined over the field K means that those coefficients, A and B, have to be elements of K. And this chosen base point corresponds to this point in projective coordinates 0, 1, 0. And the smoothness hypothesis here translates to this particular quantity, 4a cubed plus 27b squared, being non-zero. That quantity, or perhaps a scalar multiple of it, is referred to as the discriminant of the elliptic curve, and it's an important invariant. So this is what we mean by an elliptic curve. But as I say, we haven't delved that much into projective coordinates and projective space that much so far. So instead, it might be easier to think of it in just sort of normal affine space. So it turns out it is equivalent to say, well, let's just look at a normal equation in normal variables x and y. So we have the equation down here, y squared equals x cubed plus ax plus b. So we've taken a random cubic equation in x and y, we've reduced it to this. And that chosen base point is now called the point at infinity, and we denote it by this sort of curly O. And this means that if you want to talk about the point of the elliptic curve, you can actually do this without needing to think in projective coordinates. You can just say, okay, well, it's just x and y values that satisfy this equation. So if I want to look at the k points, where k is some field, the k points are just the x and y coordinates, where x and y are elements of k, that satisfy that equation. And we also have to additionally just include this extra point at infinity. So that's an elliptic curve. It's a cubic equation in projective space, but we can view that as an affine equation and then add a point at infinity, and that handles the projective thing. You meant the polynomial should be homogeneous, which of course is needed. Oh, I see. It's not homogeneous. I think, yeah, that is a typo. It should be xz squared. Good catch. Thank you very much. Yeah. So yeah, in homogeneous, if we're writing this in projective coordinates, all the terms should be homogeneous. So that x term should be xz squared. That is a typo. Thank you. Do point out typos as we go along, because they will come up and I should correct these. These notes will be made available afterwards as well through the website, as always. All right. So that's what an elliptic curve is. What does it look like? So I'm going to show you a picture, or a pair of pictures, I guess. And these pictures are kind of a cheat for many reasons, because really, when I say elliptic curve, I think an elliptic curve is the data of an equation. When I draw a picture like this, what I'm telling you is here is a set of solutions to that equation. So really, if I draw this picture, what I'd prefer to think of this as is these are pictures of the real points of some elliptic curves. The elliptic curve is just the data of the equation itself. And then this picture is a picture of the points when you look at the real solutions to that equation. All right. So on the left, you have y squared equals x cubed minus 4x. On the right, you have y squared equals x cubed minus 3x plus 3. So you can see the sort of pictures that you might get over the real numbers. One thing to point out is that these are just the affine part. So how do you think about the point at infinity? You think of it as being sort of way up the y-axis. We usually picture this at, imagine you just went infinitely far vertically up the y-axis. Actually, I should just check. Can you, if I'm fiddling around with my mouse on the screen, does that come across on the screen share? Is the mouse visible? Yeah, okay. So I might gesture around wildly with my mouse at different times. But yeah, so we imagine the point at infinity being way up here, and that is part of the curve. And these pictures come from a wonderful paper by Brown and Rice called Why Ellipses Are Not Elliptic Curves, which does raise an interesting question, like why do they get the name elliptic curve? Where does that name come from? And hopefully we will get a chance to talk about this. But there's much more to say. Why would anyone consider these gadgets? Why are we interested in cubic equations at all? There's a lot of reasons. One is that it turns out if you look at quadratic equations, that forms a class of what is called conics, which are really interesting as well. But it turns out you can always parameterize a conic. You can always give it a rational parameterization, which means that it's quite simple. Elliptic curves, you usually can't do that. Their set of rational points, well, can be pretty complicated. So they're quite interesting. Here's another reason they're interesting. Elliptic curves actually have a group structure on their points. So how do you get a group structure on the points of an elliptic curve? Well, I choose any 2 points and I want to think about a way to add them together. Well, given 2 points, I can draw a line through them. But a really powerful fact is our elliptic curves being cubic equations, if I take a line and intersect it with a cubic, that must have exactly 3 points of intersection, assuming we count with multiplicity. If it's a tangent, it might have a higher multiplicity of intersection. But there should be 3 points of intersection. And so given 2 points, I get a third point on the elliptic curve. So there's always a way to take 2 points and get a third point. And then what we do is we set that point of infinity to be the origin, the identity element of the group. And those 3 points that are on a line together, we insist that they sum to the identity element. So whatever R is, this third point of intersection, it's like the additive inverse of whatever the sum of P and Q is. Now, clearly, if I chose Q and P versus P and Q, I would get the same line. So it's evidently commutative. Turns out the hard thing to check here, if you want to go ahead and prove this as a group, is checking associativity. It's not obvious from the description at all, and it's a little involved to actually check that. But I'll just assert that, and maybe you'll believe me. So what we get is what's called an algebraic group. So what does that mean? Well, as I said, I like to think of an elliptic curve as just the data of an equation. So how do I make sense of a group structure on an equation? What I do is I say, okay, if I choose a field, I can look at the set of solutions of that field. That's my set. And then the claim is that whatever field I choose, that gets an induced group structure. So every single choice of points has a group structure on it. So going back to the picture, what can this look like? All right. So let's have a look at the left picture for a second. So I have my 2 chosen points, P and Q, and I draw a line through them, and this intersects it at a third point, which on the previous slide I was calling R. But this isn't the sum of P and Q. I claim this is the negative of the additive inverse of the sum of P and Q. So how do I calculate P plus Q itself? How do I find the additive inverse of a point? Well, what I do is I draw a line that goes through that point and the identity. Because if I have a line through that point in the identity, the third point will be the additive inverse of the sum of the other two, which is the sum of that point in the identity. So if I draw a line through this identity, which remember is way up there at infinity, so I get a vertical line, then the third point of intersection must be the inverse of this one, and therefore that's P plus Q. So if you've drawn your curve in this way, where it looks like this sort of nice picture, then you can reframe this by saying, to add 2 points, I draw the line, take the third point of intersection, which is guaranteed to exist, and then flip it across the x-axis. And you can see that being done on the right picture as well, where now I'm adding the point R to itself. So to add a point R to itself, how do I do that? How do I draw the unique line through a point itself? Well, instead, I take the tangent line to that point on the curve. So that's the line that intersects the curve at that point twice. So I take that line, intersects at a third point, reflect, and there's the sum of the point with itself. And unsurprisingly, this is called the chord and tangent method, because the chord is the line joining the 2 points. The tangent, well, that's the tangent right there. And again, these are pictures of the addition when you work on the set of real points. Okay, so in the picture, it may be surprising perhaps that any line that I draw will necessarily intersect the cubic at a third point, but this is one of the strange things that happens when you work in projective space. You do have to think about the fact that we have a point at infinity, and so for instance, this vertical line, which seems to really only intersect the curve in 2 places, really does intersect it in 3 because you have that point at infinity, which is handling all of that. So just by virtue of having a projective cubic smooth curve, we get a group structure. Every cubic curve has a group structure, which is fantastic. They are, in fact, unique among curves with this property. If you look at the space of projective curves and you want to look for the ones that have group structures, you can conversely show that they have to be elliptic curves. They have to be these cubics. Very good. So that's a story of, elliptic curves and their group structures. But as I said, we would like to, think about examples today a bit more carefully. So let's go back to that one that we started with and say, okay, I've got y squared equals x cubed plus 1. That's an elliptic curve over q, I'm going to say, because the coefficients evidently are all rational numbers at a and b here. So a is 0 and b is 1. And I claim that its q points, its rational points, are exactly the ones we worked out earlier. It's those 5 points that satisfy this affine equation plus the point at infinity. So this is a group of order 6. It's a commutative group, so it must be Z mod 6Z. And if you like, try and work out what the multiplication table for this looks like. Which of these are generators, which ones have order 2, order 3. Just add them to each other and see what sort of things pop out. The key thing to remember is that this process of adding points is not like coordinate wise addition. Oh, there's a missing comma in it, isn't here? There should be a comma between those 2 coordinates. This is quite an odd group operation. So for instance, you can work out formulae to tell you exactly what the coordinates of a sum of points is. So as an example, if I take a point xy and add it to itself, I double it, I multiply it by 2 in the group. This crazy mess is the formula for the coordinates of the output. These ridiculous rational functions in x and y. What do we mean by the only projective curves with a group structure? How do we consider all possible group structures? How do we know there's not a crazy group structure that we've not just thought about yet? It's a good question, yeah. So if you write out what it means for a projective curve to have a group structure, one of the proof is not trivial. It uses like some technology that we haven't discussed and probably we won't get to. But basically what happens is, if you want to say it in fancy language, you can prove that if you have a group structure, the canonical bundle of that curve must be trivial, which forces you to be genus 1 and hence elliptic. But that's a bunch of fancy nonsense that we don't need to worry about. But it is true that a projective curve with a group structure must be elliptic. Yeah. Good question.
Thank you.
Of course. Cool. But yeah, as I sort of intimated at the beginning, like I've been using the words elliptic curve as though these things have any right to be called elliptic. They have no evident relationship with ellipses whatsoever. An ellipse is what, like a sort of dilated circle or something. And these are cubic equations. I mean, at the very least, an ellipse is not cubic, it's a quadratic equation. So I would like to tell you this story because it's quite an interesting piece of sort of mathematical history, I guess. And it's neat to see how these ideas sort of came together. And it will actually indicate some structure and some ideas that will be useful for us going forwards. I guess one last thing I should comment on is that the calculation that we did at the beginning, or the calculation that I claimed Euler did at the beginning, doesn't necessarily immediately tell you that this is the full set of rational points. You might wonder, we computed the set of integer points, what Euler does, so you might have to think a little bit about why it is true that the rational points have only these finitely many things in them. The study, I will say, we're not going to get very deep into this today because eventually we're going to try and talk about the Weil conjectures and talk about finite fields, which are going to be much nicer. The study of elliptic curves over the rational numbers is a huge field. Lots of open questions in number theory around that topic right now. Lots of fun stuff to explore in between stuff like, ranks and BSD and, Tate-Schaff-Ravitch groups. There's like all these open questions out there that people are interested in. So elliptic curves over the rational numbers, not an easy subject. L functions, all sorts of cool stuff. All right. Cool. So why are elliptic curves called elliptic curves? Why does the word ellipse enter into this theory at all? Well, it goes back maybe even further to asking the question of how do you calculate the arc length along an ellipse? All right, so the next slide is going to have a couple of wacky formulae in it, but let me talk you through what's going on. Finding the arc length of an ellipse is a very, very ancient problem, was sort of considered by people like Apollonius to not great success. And the advent of integral calculus was a huge boon for this area. It allowed people to have a whole new lease on approaching these sorts of problems. So the way it worked is that if you start with an ellipse, say the equation is x squared over a squared plus y squared over b squared equals 1, then you introduce some variable c, some quantity that you calculate from a and b, and you can calculate that the arc length between two x coordinates, x0 and x1, say on the upper half of the ellipse, is given by this formula. This is just deduced from the usual arc length formula, which is like square root of 1 plus the derivative of f squared. So you take the upper half of this, so y becomes a function of x, you plug that in, you do some nice rearranging, and you get an arc length formula like this. This is fairly resistant to standard methods of integration. This does not have an expression using the so-called elementary functions. It's a very different sort of gadget, this one. Oh, sorry, this is a comment by Chris. This is a canonical way to turn a curve into an abelian group variety. It's Jacobian for elliptic curves over C. This is via integration, and the dimensions Jacobian variety has dimension equal to the genus. This means genus 1 curves get a group structure for free. Once you show the canonical thing you get is isomorphic to the curve. Both being one-dimensional things, this isn't so hard to check. Yes, this is a good point. For most curves, you don't have a group structure on the curve, but you have a very closely related object called the Jacobian into which the curve maps, and that has a group structure. The dimension of the Jacobian is the genus of the curve. Elliptic curves have genus 1. So you have a one-dimensional thing mapping into a one-dimensional thing. The target has a group structure. The elliptic curve gets a group structure. For other curves, you map into some higher dimensional thing, and you're some subspace which may not have a group structure on it, not a subgroup in general. So higher genus curves do map into very interesting projective varieties with group structures, though they themselves do not have a group structure. Good point. All right, back to the object here. So we have an arc length formula, which is hard. And these were dubbed by Legendre as elliptic integrals. Integrals, not just literally this one here, but integrals of this general form. He also considered other integrals that looked somewhat similar to this. maybe square root of some expression involving differences of squares or things that can be expressed using trigonometric functions. And they were an object of study. They were often approached using sort of methods of infinite series. I believe Newton actually sort of expressed the arc length of the ellipse using infinite series. Even though he had the methods of integral calculus, he kind of skirted around them using infinite series. But this led to this whole theory of elliptic integrals. And it was sort of the genius of Abel and Jacobi that said, well, hold on a second. These integrals look not dissimilar to the integral that spits out the inverse of the sine function. You might know that dx over square root 1 minus x squared gives inverse sine. And so perhaps, even if these integrals are hard to study, perhaps they are the inverses of functions that are more natural. And so, again, this is not the only integral they studied. There are various integrals, classes of integrals that were studied. But you can take the inverses of these. And the inverse of this particular function of u is called Sn, the sort of elliptic sine function. And the amazing property this sine function has is, viewed as a function on the complex numbers, it's periodic in two different ways. There are two distinct complex numbers that are linearly dependent over R, that is, their quotient is not a member of the real numbers, such that this function, the inverse of f, is periodic in each of those directions. So an integer, m and n here, I guess, and identify those are integers. So any integer multiple of omega 1 or omega 2, the function is preserved under those. Peter makes another good point about the relationship with the torus. You may be, this is a great thing about this theory. It's so beautiful, and there are so many different ways to see it that, like, everything I say you can rephrase or even predict. So, Peter, your point is prescient. We may come to this shortly. Okay, so studying, where are we at in this story? We've talked about ellipses and their arc lengths. That's led to these gadgets called elliptic integrals. And we have these inverses of the functions that come out of elliptic integrals. And the inverses of these functions have this sort of doubly periodic nature to them. They're periodic in two different directions. Functions of this kind we call elliptic functions. An elliptic function is a function on the complex numbers that is periodic in two different complex directions. All right, good. So what sort of functions do you get? Well, there are many of them, and I believe it was Eisenstein who first sort of noticed that they should have some pretty interesting properties. He, again, wrote down some infinite series expressions and noted that they should satisfy a certain relation. In fact, he said they should satisfy a differential equation of some kind. That was Eisenstein's observation. And then Weierstrass wrote down a very specific elliptic function. So here it is. So you choose this lattice, lambda, inside the complex numbers. So omega 1 and omega 2 are complex numbers, and you look at all the integer linear combinations of this. So this gives you a lattice, this discrete set of points in the complex numbers. And associated with the lattice, you get a very specific function, the Weierstrass P function, which is defined in the following way. So you have a 1 over z squared at the front, and then you sum over the non-zero elements of the lattice, 1 over z minus lambda squared minus 1 over lambda squared. You can check, based on the way this is written, that it is indeed, this function is invariant under adding any integer multiple of omega 1 or omega 2, or any combination thereof. This is invariant under this lattice. So this is an example of an elliptic function. You can also check that it is nice, it converges well defined for all complex numbers except those that are elements of the lattice. If you plug an element of the lattice into it, it will have a pole there. But at all other complex numbers that are not in the lattice, you will find that it's a nice convergent series and gives us a nice, well-defined complex function. And this complex function satisfies the following differential equation. Its derivative squared equals the function cubed minus g2 times the function minus g3, where g2 and g3 are certain invariants that you can calculate on the lattice. Given a lattice, you can calculate these g2 and g3 invariants. There's certain complex numbers depending on the lattice. But they're constants is the point. They are constants once you've fixed your lattice. And so we have here an elliptic curve. So if I write down that equation, y squared equals x cubed minus g2x minus g3, where g2 and g3 are these complex numbers, we get an isomorphism from c modulo lambda into the complex points of E by sending the point z to, well, the x coordinate is the Weierstrass p function evaluated z, and the y coordinate is the derivative. Well, Arun is here. I remember giving a talk about this at Melbourne Uni many, many years ago, and Arun very reasonably asked me, what category is this isomorphism taking place in? Which is a good question, because certainly we've been talking about things being varieties, and we're working algebraic geometry, but this map here, this Weierstrass p function, is certainly not a polynomial or a rational function. This is not an algebraic map of any kind. This is a highly transcendental function. So this isomorphism is not an isomorphism of varieties. It's a very transcendental map, but it preserves some nice things. If you give each thing an appropriate topology, this is an isomorphism of topological groups, if you like, of Lie groups, if you like, further. This topology is, in fact, a nice smooth structure, but this is certainly not an algebraic map. So
it's
we should
a holomorphic map, right?
Yes. Well, yes. So again, I mentioned this thing, you might be concerned because I mentioned that this Weierstrass p function as a function on the complex plane is not holomorphic. It has a pole, but that actually works out to be fine here because we have this nice projective curve. What ends up happening is that the map I've written down makes sense if z is not an element of the lattice. If z is in the lattice, you just send it to the point of infinity, and that gives you all the points. So yes, this is holomorphic in the appropriate sense. One other thing that I wanted to mention at this point, just to sort of marvel at the interconnectedness of all things, G2 and G3 here, these invariants that I mentioned you can calculate from the lattice, these are examples of what are called modular forms. And in fact, this discriminant that I mentioned you can calculate, 4a cubed plus 27b squared. So if you calculate that here, 4g2 cubed plus 27g3 squared, minuses in there, that quantity is a modular form. What modular form is it? Well, maybe you have to multiply by a scalar, but what that is this modular discriminant function whose coefficients are precisely the Ramanujan tau function that came up last week. In the elliptic sign case, oh, this is a good question. So there was a question about whether or not we can check this double periodicity from the fact that we know these functions are the inverses of integrals measuring arc lengths on ellipses. And that's a good question. I actually don't know how the proof goes to actually see the resulting function that inverse is doubly periodic. It may be connected to that geometry, but it is worth noting that you get elliptic functions from general elliptic integrals, which don't always necessarily correspond to exactly the arc length of an ellipse. It's just sort of a class of integrals that are related to those things. Good question. So yeah, so we have modular forms and the Ramanujan tau function somehow appearing in our picture. And we have made our journey from an ellipse to an elliptic curve via elliptic integrals and then elliptic functions. So hopefully you're not too all dazed from being browbeaten by some complex geometry there. But to give you a very nice picture of this, a picture of an elliptic curve that I sort of mentioned that picture of an elliptic curve that I drew before, the real points in an elliptic curve is maybe in various ways misleading. Well, the next picture I'm going to draw is also misleading in the similar sense that it's the set of points rather than just the data of the equation. But this picture at least has the projectivity built into it. So the picture that we get here is on the left of this little cartoon, we have the complex plane with this lattice spanned by omega 1 and omega 2 inside it. And then a picture that we may have seen many times before in topology classes. If you take the quotient of the complex plane by this lattice, what that means is that I can look at a fundamental region and identify the opposite sides of this little parallelogram. So I take two opposite sides, I wrap them around and glue them together. I get a tube, I wrap those around and glue it together, and I get a torus. So a complex elliptic curve, or the complex points of an elliptic curve, form a torus, which is really beautiful. And there is this is there are loads of ways to see this fact. The complex points of an elliptic curve form a torus. We've seen it via this Weierstrass P function. You can also see it by sort of saying, okay, well, I have this sort of compact object. What does its universal cover look like? You can say it's a Lie group. What does its Lie algebra and the exponential map look like? There's lots and lots of ways to see the fact that the complex points of an elliptic curve must form a complex torus. Beautiful story and lots of different ways to see it.
So, Angus, I guess this equality is happening, well, to go back to Arun's question, happening in the topological category. So you're saying that the topological space underlying the complex points of an elliptic curve is a torus.
Yes.
Because there's another confusing thing is that, I guess not all complex tori are holomorphically isomorphic. So we shouldn't think they're all the same.
No.
But their underlying topological space is the same.
Yes, that is a good point. Yeah, so we do consider these elliptic curves to be distinct objects. If you view them, say, as Lie groups, they are distinct based on the choice of lattice. But topologically, they are all just the same torus. And that leads into a quick topological note that if you wanted to calculate some nice topological invariants, like the Euler characteristic, or the homology or cohomology groups of this, then every elliptic curve spits out the same things. Elliptic curves always have Euler characteristic 0, which is connected to this. Oh, and also I should say, by the way, we sort of said maybe in passing that elliptic curves being cubic equations have genus 1. Well, if you think if this is the way you like to think about genus, an elliptic curve is a torus. It has genus 1 for that reason. Another reason you might say it has genus 1. So it has Euler characteristic 0 being a torus, and you can calculate the homology or cohomology groups as follows. The zeroth and second cohomology are both one-dimensional or rank 1. They're both just Z. And the middle one, H1, is Z squared, generated by each of these sort of cycles from these two sides that got glued together. Good stuff. Yes, Chris, you are right. It's not just sort of purely topologically. It's just that the group structures are different. All right. Beautiful stuff. So, ellipses, elliptic functions, elliptic integrals, elliptic curves, all connected. But this is just to give you a flavor of the language of elliptic curves and some of the things you can think about. One thing I would say is that if you are someone who's interested in learning more about elliptic curves, I think the complex picture is a really beautiful one to keep in mind, because if you can believe a statement is true for the complex case, it'll often give you either inspiration or a nice analogy in other settings over other fields where maybe the direct methods break down, but you say, well, in comparison to the complex case, I might have a sense of what's going on. Does this have to do with SL2 rep theory? Yeah, the group SL2 is very closely related to this whole story. If you wanted to look at sort of the, say, moduli space or the parameter space of all possible lattices inside the complex plane, well, there are a lot of those, but perhaps you'd notice that if two different lattices, if I give two different bases for the same lattice, I don't really want to consider those to be different. So how can I test if two lattices have the same basis? Well, it's whether there's some Z linear transformation invertible that takes me from one to the other, an element of GL2Z. It turns out, because we can always sort of scale things, we could always choose one of our basis elements of the lattice to be 1 and the other one to be in the upper half plane, so we can actually restrict to looking at SL2Z. So SL2 is very, very important for this theory as well, yes, which also, connects back to modular forms if you've studied those.
So Chris, just to clarify with Chris's, Angus, clarify with Chris's comment. So yes. I was wrong to say that they're not complex analytically isomorphic, but they're not So, but the isomorphism is not a group, like they're different as, what's the right words to say? In the category of complex Lie groups, but in the category of complex manifolds, they're all the same. Is that correct? I'm getting a bit confused with saying the right words. So
yeah, we do have to be a little careful. So the maps as Lie groups we want to consider are just induced by multiplication by a non-zero complex number on C, then you quotient out by the lattice on each side. So those are the maps that we have between these objects. If we allow more general holomorphic maps, then I imagine you can do all sorts of things. You can probably just scale any lattice to be any other lattice. But yeah, if you want to have them be the same Lie groups, then the only map has to be induced by just multiplication by a non-zero complex number. And that gives you a fairly restrictive category.
Maybe I should say that they're isomorphic as Lie groups, but not as complex Lie groups.
Ah.
For the different lattices.
So isomorphic as real Lie groups, but not as complex Lie groups?
Yes.
Uh-huh.
That's good.
Okay. So it is a bit confusing as you move around the categories.
Yes. You have to get your words quite right to make sure that we've got this nailed down. There's a good question.
Algebraically, of course, they're not isomorphic. That's the easiest one to remember somehow.
Yes.
But when you get into the analytic category, it becomes a bit harder to remember.
Certainly. And there's a really good question in the chat. Could you show an example to illustrate why these are different as Lie groups? I don't have an example that I could write down off the top of my head to sort of show here are two Lie groups that does not possess an isomorphism between them. But if that covers it for you, then that's good. Excellent. All right, goodo. So as I said, this is the sort of like story of elliptic curves of the complex numbers, which I think is a really good case to think about because it's a very concrete description. We have a very clear picture in our heads, and you can understand lots by looking at this picture. We may come back to this in the future. But what we're really interested in for the purpose of the Weil conjectures is studying things over finite fields. So what we are going to find is we gain a lot in terms of sort of computability. Things are literally finite. But perhaps intuition, it'll be helpful to have something like the complex number picture to fall back on. Okay, so let's go back to the setting of the Weil conjectures. So that says we have a variety over a finite field, and we want to count points on that and create a certain zeta function out of that. So as a reminder, this works over any finite field. So you pick some prime, you let Q be some power of that prime, and then you take X, any smooth projective variety of some fixed dimension, and the zeta function of that variety is given by this. We've seen other expressions for this as well to motivate this and relate it to zeta functions that we're familiar with. There's a way to write this as a product over closed points, which we saw in analogy with ideals, which are in analogy with prime ideals, which are in analogy with the prime numbers. So hence, this zeta function is aptly named because it's got an expression like an Euler product that the normal Riemann zeta function has. But this way is often quite convenient to work with. It's just literally the count of the rational points over the various field extensions of your finite field put into this series with Tm over m to make it look a little bit logarithmic. And then you exponentiate that. So the important thing is to be able to count points over the finite fields. So if we now look at this elliptic curve over f5, y squared equals x cubed plus 1, and we compute the f5 points, well, I mean, how many things do we have to check? There are 5 things to check for x, 5 things to check for y. We can just plug those 25 things in, and we find that of those 25 things, 5 of them work. So you can check over f5. These are all solutions to that equation. Like 2, 2. If I take 2 cubed, I get 8, which is 3, plus 1 is 4 mod 5, and then 2 squared is 4, so that's good. So I get 5 solutions to this equation, and then I add the point infinity. So there are 6 points to this elliptic curve over f5. If you now look over f25, so this is a quadratic extension of f5, well, now you have to say, okay, maybe you sort of pick some minimal polynomial for that extension, write down all of the elements, and then plug all those in. So now there's 25 squared. There's 625 pairs to consider. You plug them all into this equation, 35 of them work, and we have the point infinity. So over F25, there are 36. But already it's getting beyond the point where with pen and paper alone, it's going to be quite hard to enumerate these. So it'd be nice to have some techniques up our sleeve that allow us to enumerate points on varieties of finite fields. But if we could do that, we would be able to build the zeta function and then test the Weil conjectures. So let me just quickly remind you what the Weil conjectures are. Big full slide coming up here. All right, the Weil conjectures. So I've broken this into 4 statements this time. So the first statement is that this zeta function, this exponential of an infinite series, which is itself an infinite series. In fact, the infinite series defines us in that way is actually a rational function. It's a quotient of some polynomials. And indeed, those polynomials have integer coefficients. So that's the first thing. We have a rational function given to us by this infinite series. The zeta function also satisfies the following functional equation. So if you take the zeta function and instead of t, plug in 1 over q to the dt. So remember, q is the cardinality of our base field, d is the dimension of x. Then this is plus minus q to the d chi over 2 times t to the chi zxt, where chi is this Euler characteristic of x. Now, we haven't discussed how to calculate the Euler characteristic of a variety over a finite field. We'll have to discuss how to make sense of that at some point. And then we take our integer polynomials for point 3 and actually factor them. So we work in the complex numbers, we factor the polynomials, and they'll factor in the following form. They'll all be 1 minus wijt for the polynomial pi. And wij, what we know about it is that it's some complex number whose absolute value is exactly q to the power of I over 2. Sometimes these wij are referred to as the reciprocal roots of the polynomial, because if I just divided through by all of them, the polynomial would be t minus 1 over wij, product over those things. So it is related to, these things are the reciprocal roots of the polynomial. And then the last thing is that if our variety over a finite field, in fact, the reduction of a variety over some field of the complex numbers. So now we're living in characteristic 0. So maybe we've got a curve over Q, and in some sense, it makes sense to reduce it modulo prime P and get a curve over FP. Then, if that is the case, these BI, i.e. the degrees beta I of the polynomial PI, these degrees are precisely the Betti numbers of the variety upstairs. That is, they are the ranks of these cohomology groups, these abelian groups here. Okay, so those are the Weil conjectures. So that's what we want to test. So the first thing we might do is we might try and calculate the zeta function of a variety and see, is it a rational function? And then once we have the rational function expression, can we check all these conditions? So how are we going to do that? How are we going to calculate all of these point counts? Might be a bit hairy. Let me give you a tool that I think I have gained greatly from as a mathematician. And that tool is a bit of coding. So what I've done here is I've calculated the point counts of a particular elliptic curve using Sage. So I've chosen the elliptic curve over f5, y squared equals x cubed plus 1. We've already calculated the 6 points over f5, and I've declared that it has 36 points over f25. So let me walk you through this code in case this is something that you'd like to play around with in the future. We're going to be working in a power series ring, so Sage needs to know that. So I declare that I have a power series ring where the variable is t. QQ here is the coefficients of my power series of rational numbers. And I have to tell it what precision I want it to work to, because it can't just understand what a power series is as an infinite thing. It has to say, well, I can calculate the first some number of terms of a power series and then just sort of say the rest is plus O of whatever. So I've just set it to be 8. basically so it would fit nicely on the screen. I define the elliptic curve by saying, okay, GF5, that means the finite field, F5. And 0 and 1, this is the A and the B. So A here is 0, because it's 0 times x, plus B 1. So that defines my elliptic curve, and then I just tell it to print that out. So it tells us y squared equals x plus 1 over the finite field of size 5. Great. And then that really annoying thing to do, where you just calculate all of the coordinates and plug them into the curve to see if they work, Sage can do that very quickly. So I've just made a list here by going e.countPoints brackets 8, which means count the points over each of the extensions of F5 up to F5 to the 8. So F5, 25, 125, 625, the next one, yeah, whatever. But this is the set of numbers that you get by counting how many points it has over one of those extensions. So that 6 there is the 6 that we had before, the 36 we've seen, and then 126, 576, etc. You might already notice these are quite structured. They always seem to end in 6. That's something to notice. There's a lot of amazing things you can notice by staring at this sequence of numbers. Many people have just stared at these sequence of numbers, noticed all sorts of amazing things. But we want to package it into a zeta function. So to do that, we create that sum inside the exponential. So I've just taken the kth element of this list and multiplied it by the appropriate power of t divided by that k. One fiddly thing about Sage is that Sage says the first element of the list is the 0th element. So that's why it's k here, but k plus 1, just because Sage is off by 1 for some reason. But you just do that. You say, okay, sum all of those things together and create f. So that's this expression here. So that's the thing inside the exponential. We take the exponential of that, and we get this. This is the first 8 terms of the zeta function of this elliptic curve. So 1 plus 6t plus 36t squared plus 186t cubed, etc., 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 etc. And if this is the sort of thing you want to play around, well, you can also download Sage yourself, but you can also just very easily jump on this website and just sort of start plugging things in. And I highly recommend it. I think it's quite fun. You can find all sorts of patterns just by taking random elliptic curves over finite fields and doing point counts and calculating all sorts of things. There are also other interesting invariants to calculate as well. It's very enjoyable. Highly recommend playing around with things in Sage. As an aside, there are lots of other good resources for this. Magma is another programming language. It's very adept at working with doing computations with things like elliptic curves. You can also, use websites where people have compiled lots of the data of elliptic curves and related objects. For instance, the LMFDB is a cool resource for this sort of stuff. But regardless, what we have calculated is the zeta function has these first few terms. You can cut off the 6 and the 7 just for this, but it's just some big sum. It's a big infinite series. And what we want to do is recognize this as a rational function. I don't know about any of you, but to me, this is highly non-obvious. Maybe some of you are very adept at infinite series, and you can immediately say, aha, I can totally see how to factorize that into a quotient of polynomials. But for me, it is not at all obvious. So to make our lives easier, we're going to use a clever little heuristic. I should pause and just check the chat and see if anyone has any questions. When is the form series power rational function discussed? Aha, yeah, very good. So there are general methods for doing this. There are good ways to check and form match as a rational function. All right, I'll show you one way that things are going to get easier for us. So one thing to notice is that how many points could this elliptic curve have, really? Well, first of all, over the finite, imagine you plug in a particular x value. Well, what you're requiring is that x value, when you plug it into this, x cubed plus 1, it spits out a perfect square inside F5. That's what we need. We need some number cubed plus 1 to equal a perfect square in F5. So how many points might you expect roughly? So here's the heuristic argument. Roughly, half the numbers in fq to the m are perfect squares. I say roughly, it's not exactly right because the size of fq to the, this is an odd cardinality set. 0 is a square. If you take out 0 and you look at the non-zero elements, then half of them are perfect squares. So half the non-zeros are perfect squares, and then 0 is also perfect square. So, you know, half of these plus 0.5 are perfect squares. If you imagine that plugging in an x value to this polynomial, this cube polynomial, is essentially a sort of random process. X cubed plus ax plus b essentially is a random element of this finite field. Then you might expect, if I'm just hitting numbers that randomly, I should expect to get a square about half the time. And if I do get a square, I expect to get 2 points corresponding to that. One corresponding to positive y and one corresponding to negative y. So the point count we expect heuristically to be 1 plus 2 times, well, so that we get half the elements being squares, and then for each one we get 2 points. And then there's some error term over here, epsilon q to the m. So how many q to the m points are there? There's 1 plus q to the m, the size of this over 2 times 2, plus epsilon q to the m. And you can actually like deal with the 0 issue. You say, okay, well, really I should be subtracting 1 here because of the 0. But if I did get 0, then there is actually only 1 point corresponding to 0. Because if x cubed plus ax plus b is 0, then you don't get a plus or minus y. Y just has to be 0. So really there should be a sort of, there should be number f q to the m minus 1 over 2 times 2, and then plus another 1 out here. But whatever, you get the same thing. 1 plus q to the m plus some error term. Very interesting question of how close is this to the actual point count? Can the error be very large? Is it always around 1 plus q to the m plus not very much? But we'll come to that. But for the moment, what I'd like you to notice is that if we just look at the expression for the zeta function, it's the exponential of the sum of this number, which we've now expressed as the sum of 3 things. So I factor that into the exponential of, okay, this is the 1 term, this is the q to the m term, and this is the sort of term with this error, this epsilon left over. So this infinite series, t to the m over m, that's negative log of 1 minus t. This middle one is negative log of 1 minus qt. And so exponentiating, I just get 1 over 1 minus t times 1 minus qt times the exponential of the series with this error term. So what I'd like to do now is say, okay, well, maybe we expect that our zeta function should factor like this. And maybe this last term might be easy to understand, might be easy to recognize. So let's try that. Let's say, okay, I've got a factorization, and maybe this last thing will be an easy rational function to recognize. This exponential of this sort of series made up of the error terms. So we'll go and do that. So we're going to take the point counts and subtract off 1 plus q to the m from them. So I go back to Sage. I've defined, it's the same E as before. So now all I've done is I've made a new sequence where instead of just counting the points, I take the point count and then I subtract off the 5 to the n minus 1. Again, we have to do this shift thing because of the indexing in Sage. And we get this sequence. Very fascinating collection of numbers here. 0, 10, 0, minus 50, 0, 250, 0, minus 1250. Something very special is going on. And a lot can be said about that. But for our money right now, what we're interested in is plugging these in as the coefficients of our infinite series to get this gadget, and then exponentiating, and oh, look at that. It's just 1 plus 5t squared plus a bunch of nothing. All the higher terms are just 0. Nothing is coming up. Now, this could just be a precision error. I'm only calculating up to t to the 7, really. Everything t to the 8 and above is just disappearing. So you could totally believe that really this is not actually a polynomial here. Maybe there are higher terms. But this at least suggests to us that perhaps our zeta function should factorize as 1 over 1 minus t times 1 minus 5t. That's the qt term. So these are 2 terms in the denominator that we factored out before. And then that epsilon bit, it's just a polynomial. It's just 1 plus 5t squared. And there that is there. So this suggests that the zeta function of our elliptic curve might be of this form. And as I say, highly encourage you to play around with this yourself. Go much beyond 8. You can go much, much higher and convince yourself of similar things. This is one example. I must give you another. I am implored to give you another. So here is a second example. We'll now work over a power of p, where we're picking p equals 7. We're working over f49. We've got the elliptic curve y squared equals x cubed plus x plus 1. So we set out that elliptic curve. We calculate this sort of sequence of error terms. Okay, again, maybe a pretty interesting sequence, but not as anything obvious jumping out to us as last time. We calculate the series associated to that. We exponentiate, and once again, we're getting something that looks very much like a polynomial, suggesting that in this example, the zeta function should just be 1 plus 5t plus 49t squared over 1 minus t, 1 minus 49t. It's fascinating to play with this just to see what happens. For instance, how different is this if you replace 49 with 7? This is clearly, this curve clearly doesn't need to be defined over 49. I'm not using any elements of the extension. This could be defined over f7 if you wanted. And it's interesting to compare. Or take the previous one, just x cubed plus 1 over f7. What happens there? Is that a reasonable curve to study? So this suggests a sort of specialized version of the Weil conjectures for elliptic curves. It looks like elliptic curves, their zeta functions are some quadratic polynomial of a very special form. It's 1 plus something times t. Last time it was 0, this time it was 5. Plus q, the cardinality of the base field, times t squared. That's our numerator, and denominator is always of this form. Let's check if we believe that to be true, that it would give us the Weil conjectures. So this coefficient here, we'll call that a sub q. And I should notice, by the way, that this a sub q is exactly the first of those error terms. If you looked at those error terms epsilon, you looked at epsilon sub q, it's exactly a sub q. If you just expand this out into a series again and match up the terms, you'll find this exactly gets attached to that error term. So that first error term, the difference between the point count and 1 plus q, turns out to be very important. It sort of determines everything else. Kind of tells you that if you believe this, then if I have an elliptic curve over a finite field and I know the point count over that base field, then I should be able to deduce the point counts over every other field extension of that finite field. So if I know the point count over fq, I should somehow, by unpacking this series, be able to deduce the point counts over fq squared, fq cubed, etc., which is interesting. But let's check that the Weil if we did believe this, would the Weil conjectures hold? So first of all, this is a rational function, tick. I did spend a little time checking that you can do \check mark using AMS Simb, so that's great. Thank you, LaTeX. The Euler characteristic for elliptic curves is 0, which again, I haven't really made sense of that for an elliptic curve over a finite field. But if you believe it's true for elliptic curve over the complex numbers, maybe you believe that whatever the definition is matches up nicely. So I will tell you the elliptic curve has Euler characteristic 0. Therefore, the functional equation we expect, given that it's Euler characteristic 0, is that when I plug in 1 over qt, because the d is 1, dimension is 1, I should just get the original zeta function back. Oh, that x should be an e. That's it. That should be an e. So I plug in 1 over qt. I do this. And then, well, I haven't done out all the algebra for you, but just multiply through by qt everywhere. You'll get a sort of q squared and the numerator and denominator canceling out, and you will get exactly the same thing back. So it's equal to this. There is no sort of correction term in the functional equation. It is just equal to this, which is what we expect in the Euler characteristic 0 case. Now we need to check this third thing about the size of these reciprocal roots, the Riemann hypothesis, as it's called. Well, the case of 1 minus t and 1 minus qt, that works. because 1 minus t is the 0th part. So we expect it to be, that coefficient of t should be size q to the 0. It is, it's 1. This one should be size q to the 2 over 2. It is, it's q. So the interesting one to check is p1, the numerator. So P1 is this numerator term. It's 1 plus AQT plus QT squared. And so we factorize that in some way. But it's maybe not immediately obvious just by knowing that this is a quadratic that these have the right property. We maybe can say something about them. We can see what they must add to negative AQ. They must multiply to Q. So there's something going on there. But we can't immediately deduce they are of the correct size. The fourth point to check is these sort of degrees and this Betti number stuff. Well, the degrees are 1, 2 for P1 and 1 for P2. And yes, we saw that if you're in characteristic 0, the complex points are a torus. So these are exactly the rank, the dimensions of this cohomology group. It matches up perfectly. 1, 2, 1, exactly as we expect. So the only real thing that's sort of lingering, the only real issue that we're having here is the Weil conjecture that maybe is the most interesting to some people, which is, well, the Riemann hypothesis. So what might make you believe that to be true? Well, let's just dig into this for a moment and see what we get. So as I mentioned, if you add these two roots of P1, you get negative AP. If I multiply the two roots, I get Q. So if we knew the Riemann hypothesis, if we knew that their sizes were Q to, okay, this is I is 1, so Q to the 1/2, root Q, then the size of AP, okay, I've got to mix up between A, that P should be a Q, I guess. But the size of this AQ should be, by the triangle inequality, less than or equal to 2 root Q. Remember, this is that error term that I was talking about, how different the true point count is from the quantity 1 plus Q. And this bound on that difference is called the Hasse-Weil bound. First proved by Hasse for elliptic curves, generalized by Weil to curves in general, and is one of the lenses through which the Weil conjectures in general were viewed. This Hasse-Weil bound turns out to be its truth turns out to be very closely related to this Riemann hypothesis. So we have a way of maybe testing our conjectures. We can build elliptic curves and count their points. We have a form that we expect the zeta function to be in now. So all that's left to know is how do you actually prove these Weil conjectures in this case? And maybe I'll leave you hanging on that. And thanks everyone for listening. That's all I got for you today. The one thing I didn't do, I didn't have enough photographs of old mathematicians to post on the slides. I should have had some photographs of like Euler and Legendre and Jacobi, certainly. I was not following Masoud's example well.
So can we, so I guess in general, it's too much to expect that one has a formula for this AQ.
What would you mean a formula?
Well, you have let's say your elliptic curve is given by x cubed equals, y equals x squared, x cubed plus alpha x plus beta.
I see.
So then you can ask, well, there is an AQ. Can we write down the formula for AQ given alpha and beta and
right.
Q?
Yeah.
But I think maybe your example is suggesting that this is too hard to do in general.
Yes. Certainly, were any such formula to exist, I mean, I can't imagine what a closed formula for that would look like. We have an algorithm to calculate that. That's just calculate the points of the finite field. But getting an actual, like, a function that you could express in elementary means that you plug A and B into it, spits out, or alpha and beta, and it spits out this AP quantity. That's unclear. Great. The first two examples seem to have a different number of components. Is there an invariant of E for this? Oh, so you mean the very first picture of the over the real numbers? How they had different numbers of connected components? Yeah, that's a good question. So I should comment that it does obviously depend. When I say connected components, it does depend a little bit on what sort of topology you give your space. But yeah, I would say visually, let me just swing back to that slide. But yeah, visually, certainly these two look like they have different components. And you're right, there is an invariant that can be calculated here. And it turns out the elliptic curve has, over the real numbers, either one or two components. That's the situation that you could get. I cannot remember off the top of my head how you determine which is which, but there is an invariant that's not hard to calculate that will tell you that, I believe. Good question.
Well, if it's in Legendre form, you just count the number of real roots.
That's the one. There you go. There it is. Yeah, you calculate the real roots in Legendre form. Thank you. Because it is determined by how many times it passes through the axis. Exactly. If it passes the axis once, it's just.
I think that's actually not Legendre form. This is, I mean, Weierstrass form, right?
Yeah.
The one you used.
Yeah. Y squared equals a cubic. You're right. Yeah, that is exactly it, because you're literally asking. Yeah. So, okay, it's not complicated. It's look at the picture. What's the difference? Well, the one that has one component goes through the real, the x-axis once. The other one touches the x-axis 3 times. So you just look at the expression as y squared equals a cubic in x, and then you just ask, how many real roots does that cubic in x have? The left one, x cubed minus 4x, has 3 real roots. The right one has 1 real root, and that's how you tell. So yeah, thank you, Peter. That is it.
I guess a more intrinsic way is to look at the 2 torsion and see what it is over the real numbers.
Yes, that is a way that would not depend on the choice of equation.
Thank you very much, Angus.
Thank you.
So you will continue then next week to tell us the proof.
Yes.
Or outline the proof.
Sorry. Elliptic curves over finite fields, very rich subject. I haven't talked at all about Tate modules or Frobenius or endomorphisms. There's lots of stuff to talk about, so we'll do all of that. Isogenies, torsion, big story. Thanks everyone.
A lot.